Aurora Borealis, the northern sky ablaze in dazzling grandeur as charged particles from the sun, trapped in the Earth's magnetic field, crash into the gases of the atmosphere, exciting them to luminescence. Fortunately for us, the magnetic field deflects most of the solar wind safely around and past the Earth. The great mystery is how the Earth's magnetic field is generated. That mystery, though, has diminished markedly by the new understanding I recently published in the scientific literature, and which I share in this video. Earth's magnetic field is all around us, but it's invisible. You get a sense of how it might appear by sprinkling iron filings on a piece of cardboard with a magnet held beneath it. The iron filings align themselves with the magnetic field. More than 1,000 years ago, individuals in China discovered that slivers of lodestone, a natural magnet, floated in a bowl of water, quickly assumed a preferred position. That observation led to the development of the magnetic compass, a real bonanza for navigators and hikers. In 1600, William Gilbert published a major compilation of magnetic measurements from around the globe. These showed that the Earth itself is like a giant magnet, rather than the magnetism arising from an unknown extraterrestrial source, as supposed by some. About 200 years later, Gauss put those magnetic measurements into a mathematical form, showing that the source of Earth's magnetism is at or very near the center of the Earth. The Earth acts as if it has a bar magnet at its center, but it can't. Inside Earth is too hot for permanent magnets. Moreover, interactions with matter of the Earth drain energy from the magnetic field. This means that some mechanism must exist near the center to produce the Earth's magnetic field, and an energy source must exist to continuously power it. In 1939, Walter Elsasser published his idea that the Earth's magnetic field is generated by a dynamo mechanism in the Earth's fluid core. His idea is now the stuff of textbooks, but there are problems, serious problems. Elsasser knew that the iron alloy of the Earth's fluid core conducts electricity. He imagined that heat produced at the base of the core would cause convection in the fluid, which would be twisted by the Earth's rotation, producing a dynamo mechanism, a magnetic amplifier. Superficially, at least, that seemed to make sense to the geoscience community for nearly 70 years. But look closely. Watch the celery seeds, dragged along by the flow of water, heated in a beaker on a regulated hot plate. This is convection. Now I covered the beaker with a piece of ceramic tile. Watch what happens to the convection. When a fluid is heated from beneath, it expands, becoming lighter, less dense than the fluid above it. This top-heavy arrangement is unstable, so fluid motions result as the fluid attempts to restore stability. The top-heavy arrangement occurs because the temperature at the bottom is hotter than at the top. By covering the top with ceramic tile, I am preventing heat loss from the top, minimizing the difference in temperature between the top and the bottom, which drives convection. See? Watch. In less than 2 minutes, the convection has slowed markedly. For long-term stable convection, the heat brought from the bottom by convection must be removed efficiently from the top. The ceramic tile prevents that from happening. From rock magnetism, we know that the Earth's magnetic field has existed for at least 3.5 billion years. Except for reversals of polarity, the geomagnetic field has been remarkably stable for long periods of time, times as long as 40 million years. So, what's wrong with Elsasser's idea? Like the ceramic tile atop the beaker, the Earth's fluid core is wrapped in an insulating blanket, a rock shell that is 2,900 kilometers thick. Rock holds less heat, and it conducts it more slowly than the iron alloy core. Thus, heat brought to the top of the core cannot be efficiently removed. In other words, the bottom of the core cannot remain significantly hotter than the top of the core for long periods of time, and thus convection in the core likewise cannot be sustained for long periods. The implication is quite clear. Either the Earth's magnetic field is generated by a process other than the convection-driven dynamo mechanism, or there exists another fluid region within the deep interior of Earth which can, in fact, sustain convection for extended periods of time. The latter appears to be the case. In 1993, I published the first of a series of scientific articles revealing the background, feasibility, and evidence of a natural nuclear fission reactor called the georeactor at the center of the Earth as the energy source for the geomagnetic field. In 2007, I published evidence in support of the idea that part of the georeactor is a fluid, and in that fluid the Earth's magnetic field is generated by convection-driven dynamo action. The georeactor, deep within the inner core of the Earth, consists essentially of two parts. The uranium subcore lies at the very center. This is where nuclear fission chain reactions take place that produce the heat. The electrically conducting fluid subshells surrounding the nuclear subcore consist of fission products and products of radioactive decay. The nuclear subcore heats the fluid at the bottom of the subshell, making it lighter, less dense than the cooler fluid at the top. This top-heavy arrangement is unstable, resulting in convection motions of the fluid, which are twisted by the Earth's rotation, creating a dynamo, a magnetic amplifier. Heat brought to the top of the subshell by convection is efficiently removed by the massive thermally conducting heat sink that is the inner core, which is surrounded by an even more massive heat sink, the fluid core. This arrangement assures long-term stable convection within the subshell. The georeactor unit acts as both energy source and convection-driven dynamo mechanism for generating the Earth's magnetic field with no impediments to long-term stable convection. Moreover, neutron-rich radioactive fission products in the subshell assure numerous sources of electrons that can produce magnetic seed fields for the dynamo to amplify. 6 planets and one of Jupiter's moons currently possess internally generated magnetic fields. Our moon and Mars have magnetized areas on their surfaces which seem to indicate the past existence of internally generated magnetic fields. I have suggested georeactor-like nuclear fission reactors are common features of large solar system planetary bodies and are thus responsible for generating and powering their magnetic fields. Science is about discovering the true nature of Earth and universe and sharing that knowledge with people everywhere. That's what I do. My name is Marvin Herndon. I hope you've enjoyed this video. Please visit my website, nuclearplanet.com, for more information and references.